Okay, good morning, Algebra 2 Trig Honors students. So this one is the continuations of Chapter 4 lecture. So for the first half of the lecture, we actually talk about number 16 for the last problem. So the way that I did it might be a little bit different because I'm using the P over Q theorem, the rational zero theorem, to find out the rest of the real roots. Okay, so now another way you can do it with finding the rational real roots. So here's something that I would like to introduce. Okay, so this one is called the conjugate theorem. So one thing that you guys already know from Algebra 1 is that a squared minus b squared. So once you factor it, it's like a minus b times a plus b. So let's say that a minus b is the given conjugate. So that means the hidden conjugate would be considered a plus b. So for the conjugate theorem of a polynomial, so let's say that if we do have a plus bi with the given complex root, the given, you can say the complex or the imaginary root. So that means the hidden root for this one would be a minus bi. Okay, so this one is hidden, the hidden root. Okay, so now let's do one example like this. So for number 18, so since we do know that negative 4 plus 2i, so that's a given imaginary root. So that means its conjugate, negative 4 minus 2i. So that would be the hidden root. Okay. So one thing that you want to find out before you find the rest of the rational zero, so you want to start out with the divisor. Because once we find a divisor, we can just using that as the denominator, so we can divide it from the polynomial, so we can get a quotient. So once you get a quotient, you can factor it, so you can get the rest of the rational zero. So for the divisor, the way to set it up is x minus the quantity of negative 4 plus 2i in group, and then the other one here, x minus the quantity of negative 4 minus 2i. So again, just put it in group. And now for the rest of this, so we just regroup them. So we do have x plus 4 minus 2i, because negative times positive, then that'll be negative. And then for the second group here, so we do have x plus 4, quite similar. And then negative times negative, positive, plus 2i. So once you multiply it out, so this one is just a pattern of difference of two squares. So it's like a minus b times a plus b. So that means this one is under the structure of a squared minus b squared. So that would be written as x plus 4 quantity square minus 2i quantity square. So try to expand it. So we do have x squared plus ax plus 16. And then 2i squared, that would be 4i squared. So that's negative 4 times negative 1, so positive 4. So the divisor is considered x squared plus ax plus 20. As you can see that there's no more imaginary number involved. So now, what we need to do after that, so we just want to divide this long polynomial by the divisor. So that's something I have done previously, but let me explain what I have right here. So for number 18, so the dividend, so we do have 2x to the power 5 plus 15x to the power 4 plus 26x to the power 3, and then the rest of those terms. And now you want to divide it by x squared plus ax plus 20. So first thing that you want to multiply is that the terms and the number, that you can cancel out that 2x to the power 5. So what I did, I multiplied by 2x to the power 3. So 2x to the power 3 times x squared, so that will give you negative 2x to the power 5. And then the rest of those terms, just distribute, find out the product. So 2x to the power 3 times ax, positive 16x to the power 4. 2x to the power 3 times 20, positive 40x to the power 3. So for the remainder, all you need to do is just subtract. Anytime that you subtract, you always want to cancel out the first pair of those terms. So the first pair got canceled, so we got 15x to the power 4 minus 16x to the power 4, so it's negative x to the power 4. And then the rest of this, minus 14x to the power 3. So once you get this part right here, you want to bring down the next term, because that's a trinomial divided by the trinomial. And then the next term that I put up here, it's negative x squared, because once I multiplied it, so I get negative x to the power 4. And then those rest of the term distribute, and then multiplied it out, so you get those negative ax to the power 3 minus 20x squared. Once you subtract this, so you'll get the remainder, negative 6x to the power 3 minus 48x squared. And then finally, you want to bring down negative 120x, and then you multiply that by negative 6x, because eventually everything will get cancelled. So once you see everything get cancelled, so that means the final remainder is 0. So once we come up with the quotient, so the rest of this, all you need to do is just find out the rest of the rational zeros. So for the quotient, so we can take out the greatest common factor, which is x. And then the rest of this, 2x squared minus x minus 6. And now you want to factor the trinomial. So we do have 2x, 1x, 3, negative 2 with the smiley face or the factor tree. And then put this all together, so we do have x times the quantity of 2x plus 3 times the quantity of x minus 2. And then you want to set that equal to 0. So solve for x. So we do have x equals 0. X equals negative 3 half for the second factor. And then the third factor, we do have x equals 2. And don't forget about the original imaginary solution. So we do have negative 4 plus 2i and negative 4 minus 2i. And once you count them all together, so totally we do have 1, 2, 3, 3 real and 2 imaginary solution. So the total number, that would be 5, because the highest power is 5. Now let's take a look at that, number 20. So number 20 is quite similar to this one. So back to the packet. So number 20. This one, there's no imaginary number. So the one that's given is called the irrational root. Irrational, because that once you take the square root of 13, it's going to be irrational number. It's the non-terminating decimal. So again, this one is considered the given root. And for the conjugate, so that would be considered 3 minus root 13. So what I did, I just applied the conjugate theorem to find out the other root, so the hidden root. So once you multiplied it out, so this one set up the divisor. So you'll get x minus the quantity of 3 plus root 13 multiplied by x minus the quantity of 3 minus root 13. And this one should be showing that on the active inspire, the one that I did previously. Okay, so once you multiplied it out, so you end up with x minus 4 quantity square minus 10. So what I did here, I just regrouped them. So once you regroup, you'll see that it's a difference of 2 squared pattern. And then the rest of this, so just expand it and then combine the like terms. So eventually you'll end up with x squared minus ax plus 6. So that's the divisor. So again, going through the long division process, so you want to put in that trinomial versus trinomial. So start it off with x to the power 5 times x squared, so you get x to the power 7. And then the rest of the term, you just want to distribute. Find out the product, and then put it underneath that dividend here. And then subtract. So this one got cancelled, so x to the power 7 got cancelled. And then negative 5x to the power of 6 minus negative ax to the power of 6. So that would be 3x to the power of 6. Because negative times negative, that would be positive 8x to the power of 6. Subtract, so you end up with 3x to the power of 6. And then the rest of those terms, subtract, and then bring down another extra term. So once you keep doing all this, so eventually you'll end up with the remainder, which is 0. If you find out the remainder, it's not 0, so that means you probably end up with something wrong, okay? So the first time that I did it earlier, so I end up with something that is kind of like a weird number. So now, for those you might be wondering, what would you do with the rest of the quotient after you finish the long division process? Again, the quotient, it's non-factorable. So if the quotient is non-factorable, another thing we can do is it's called the P over Q theorem, the one that we talked about yesterday, the rational zero theorem. So now let me just put it into the next slide. So what we found for the quotient is x to the power 5 plus 3x to the power 4 plus 2x to the power 3 plus 6x squared minus 15x and then minus 45. So now this one is still considered a long polynomial. So what we can do, we can just analyze it by finding out the constant term, which is what, negative 45, and then the leading coefficient, which is 1. And now we need to find out the possible factors of negative 45 and the possible factors of 1. So we do have plus minus 1, plus minus 3, plus minus 5, plus minus 15, and then plus minus 45. So those are the possible factors of negative 45. So the possible factors of negative 45. And then what about for 1? So we do the same thing, possible factors. So we only have what? Plus minus 1. So possible factors of positive 1. And now once you divide it, so you do have plus minus 1, plus minus 3, plus minus 5, plus minus 15, and plus minus 45 again. So what this tells you here, it's all about the possible root, the possible rational root. Okay, so now the next thing that you want to do, you want to perform the synthetic division with the quotient. So let's just bring down the coefficient. We got 1, 3, 2, 6, negative 15, negative 45. So basically just simply bring down all the coefficient here. And, well, you might be wondering, there's so many options. We can choose 1, negative 1, 3, negative 3, 5, negative 5, and so on. So which one should we verify first? And as you can see that the number here, we do have 3, 6, 15, 45. So the majority of the number here that is showing 3 would be considered the greatest common factor for all those numbers. So let's just start it with either 3 or negative 3. But let's try to start it with a negative number first, negative 3. So trial number 1. So let's start it with x equals negative 3. So once we divide it, the first number you don't want to do anything. You want to bring it down. So 1 times negative 3, then that'll be negative 3. So for synthetic division, you want to add those numbers to get the new remainder. So we got 0. And then go through the same process. Negative 3 times 0, or 0 times negative 3. So we do have 0. And then combine them. So we do have 2. 2 times negative 3, then that'll be negative 6. Combine them. So 0. 0 times negative 3. So 0. Bring down negative 15. Negative 15 times negative 3, so positive 45. Combine them, so eventually, so the remainder is 0. Again, so anytime that you perform the synthetic division with finding the rational roots, always the remainder is considered 0. Again, this one is considered negative 15. Okay, so now what can we do with the rest of this? So let's just rewrite it with the normal polynomial. So again, it's always considered 1 degree less. So 1x to the power 4. So there's no 0x to the power 3. So we just bring down 2. So positive 2x squared. And there's no linear term right here. So bring down negative 15. And now for the rest of this, so we can find out the rest of the rational roots. Okay. So it looks like this one, it's factorable. So we try to factor it. So we do have x squared plus 5. And then x squared minus 3. Okay, so it looks like this one we can find out 4 rational or irrational roots. Okay, so this one here we do have x equals negative 3, so that's considered one of those roots. Okay, keep that in mind. And then once you solve for this, so we do have x equals plus minus root 5. Okay, because that once you isolate that negative 5, well, it's actually plus minus root 5i. That would be another imaginary solution. And then for this one here, then that would be considered x equals plus minus root 3. Okay, so we do have 1, 2, 3, 4, 5 roots already. So 3 real, and then the other 3 real, and the other 4 they're considered imaginary. Okay, so going back to the previous slide here. So we do have this one as well, 4 plus root 10, 4 minus root 10. Well, it's actually considered 2 imaginary and then 5 real. So 4 plus root 10, so this one's called the irrational root. There's no imaginary number here. So 2 irrational, 4 irrational, 1 rational, and then 2 imaginary. So all together, so that would be what? 7 solution. 7 zeros. Here we started out with the original long division here. So 7, the highest power. So 7 0. So once again, 1, 2, irrational. 3, 4, irrational. So 4 irrational, 1 rational, and 2 imaginary. It is a little bit complicated, so by the time you're doing it, so you need to slow things down. So what about any problem like this on a test? Well, probably not. Or maybe something it's going to be a little bit easier because this one is like time consuming. So you have to do both the long division and also you have to go through P over Q with the synthetic division. So now let's see what else that we have for the rest of the lesson here. So we went over 18 and 20. So now 22, 23. So those are the ones that are quite similar to what we have done for the first half of the lesson, which is the first set of the problem. So once you put it into decimal, you'll see that you can find the 0, you can find the x-intercept, the y-intercept, and also you can do the end behavior. So this one basically just put it into decimal so you can see that the graph. So refer back to the first video, the one that I showed you already. And now what about for 24, 25, 26, 27? So this one is basically setting up the polynomial. So like 24. So what we need to do, so the roots, they're all given already. So what we can do here, we can just set up the linear factor. So -4, so that means it's x plus 4. 5/2, so that means it's x minus 5/2. And then 4/3, so that means it's x minus 4/3. And then the rest of this, all you need to do, just FOIL. Again, the way that I show you FOIL is something that I show you from the first video, the first half of the lesson for chapter 4. So binomial, multiply by the binomial. And then once you get the trinomial, you want to multiply by the other binomial. And now what about for 26? Now got to be careful with 26. It looks like we do have only 2 roots. One real and the other one is imaginary. Again, anytime that you see the structure, if that's considered imaginary or the rational, the radical, so that means you need to set up the conjugate. So the conjugate for this would be the hidden root. So -3 plus 2i. And then once you set up the polynomial, so that would be considered p of x. So that equals x plus 1/2 times x minus the quantity of -3 minus 2i. And then times the quantity of x minus the quantity of -3 plus 2i. Again, the rest of this, you probably want to multiply the conjugate first. So using that regrouping method, and then difference of 2 square. And once you get the trinomial, you can multiply that with the binomial. So eventually, that's going to be the standard form of p of x. So finally, we're getting down to 28, 29. So for 28, so evaluate each function with the given value. So a lot of people might be thinking about that 28 is just like f of -7. So we just need to plug in -7 to the whole equation. Now the things that you can do it that way, but you try to do it that way, it's going to be a little bit tedious because there's so many power, there's so many terms involved. So what we can do, we can use the remainder theorem to solve for the problem. So now let me talk about the remainder theorem. There's so many theorems for this chapter here. So remainder. So anytime that you find out the remainder by doing the synthetic divisions or the long division. So that number, so let's say that c is the remainder. So we want to evaluate f of c. So where c is the remainder. Let's see. Okay, let's say f of x or f of a, f of x. So let's say that the function is f of m or f of x. So that's just original functions. F of x with the value of c. Okay, so I don't want to put in c as the remainder yet. Okay, let me just change that. So this one is the theorem. Let me just introduce that once again. So let's say that we do have f of c. Well, c is not the remainder. C is just a divisor. So where c is the divisor. So once you go through the long division or the synthetic division, So you'll find out the remainder. Okay, f of c is given. So where c is the divisor. So once you find out, okay, when you find out the remainder, so the remainder of either the synthetic or the long division you perform will be the result of the value f of c. So let's say that the remainder, it's r. So whatever the remainder that is, so that's going to be the final results of f of c. So now let's do one example like this. So what we have here, the value of c, which is what, -7. So now let's perform the long division or the synthetic division. I'm sure you guys like the synthetic division better. So let's take out the coefficients. So we got 1, 5, -8, 48, and then 43, and then -2. And then the divisor, which is the value of c. So -7. So now let's find out the remainder for this. So the first number, bring it down. So 1 times -7, -7 plus 5. So that would be what? -2. So -2 plus -2 times -7. So it's 14 plus -8. So that would be what? 6. So 6 times -7. So -42 plus 48. So that would be considered 6 once again. So 6 times -47. So that would be -42. Combine them, so it's 1. 1 times -7, so -7. So -7 plus -2, so -9. And guess what that number is? So -9, so that would be the final results of f of -7. Okay? So how do I verify this? You can always plug in a number and then just put it into the calculator and find out exactly what that is. So eventually the result is -9. So let's check this. Number 28 down the bottom. So the solution right here, -9. Okay, so that's it. So anytime that you do have question regarding this, so welcome to come to my office hour or the after school tutoring on Monday, Tuesday, and Thursday. And you're more than welcome to watch the video over and over again. Okay, so anything that I need more time to digest or understand it, so always you can press the pause button, or you can always rewind it or fast forward. Alright, so thank you for watching the video today. So I'll see you guys next time. Take care.